Thank you. Thank you very much for coming to my talk this morning. Mornings are hard, right? So, my name is Ignat. I work for Cloudflare. Who here knows about Cloudflare? Then I won't explain what we do. And today I'm going to talk about it's kind of like unfinished research about TPMs and its integration to the Linux kernel. So a little bit about myself. Yes, I do Linux at Cloudflare, mostly working on the kernel. I'm passionate about system security and performance, and I enjoy low-level programming, Linux kernel drivers, bootloaders, and other stuff written in unsafe languages. So, a quick recap. Who here doesn't know what a TPM is? So everyone knows. That's a very specialized event. But yeah, a quick recap is a TPM is a small security chip present in most modern laptops and even servers. And I wrote it's a discrete security chip, but like sometimes it's also embedded like system on chip, or modern CPUs actually have embedded TPMs. But the nice thing about it is it's a cheap, passive, non-intrusive device. It only responds to the commands and performs cryptographic services. But the presence of this chip allows us to have good foundations for platform security, authentication, and most importantly, remote attestation. And as a good security chip, it can handle cryptographic keys, which will be the focus of our talk today. Yeah, so in this presentation, like when we talk, usually people talk about TPMs, we talk about platform integrity or remote attestation, which is a primary feature. But like I will be talking about TPMs from an application developer perspective. So like imagine if I write some applications running on Linux and I know every modern piece of hardware has a TPM and my application needs to perform cryptographic operations, can I actually use the TPM for that to have better security, right, to handle my cryptographic keys? And it would be nice not to expose my cryptographic keys to my main application memory, because that always ends up badly. Who here remembers Heartbleed? Log4j, other stuff. There's so many, like having keys in your main application memory is not that great. So like using some kind of different approach is much better, and at least you can prevent leaks of your cryptographic keys, right? So yeah, I'm an application developer. I want to use TPM. I know it's there. It's always there. So can I just use it? Well, no, right? Because my application runs on an operating system, and usually you can't directly access hardware. You need to go through some operating system abstraction, and in Linux you have this virtual device file dev tpm0. So, okay, I can talk to TPM through that device. Well, not exactly, right? I also need a thing called resource manager. TPMs, the advantage of TPMs, they're cheap devices, so they're everywhere, but the disadvantage is they're not very powerful, and they do not actually support concurrent access from many processes, and modern Linux operating system are multitasking operating system, and probably eventually every process wants to use a TPM, so you need some kind of entity which will mediate and serialize access to the TPM from all these applications. So this is called a resource manager. But good, right? So it's not enough as well, like to talk to the resource manager. I probably want to use some kind of TPM library, because I don't want to re-implement like communication from scratch and read the gazillions of pages of TPM and trusted computing group specifications. But even that, it's not always enough. If we zoom into the resource manager, well, traditionally the resource manager was implemented as a daemon, a service on the operating system, which creates confusion on its own. So now, basically, to access the hardware, you need some service running. And what if you misconfigured your operating system and you didn't start that service, or the service crashed for whatever reason? Like, okay, suddenly you don't understand why you can't access the hardware because some service is not running. Modern Linux operating system realized that, and they kind of re-implemented the resource manager inside the kernel. So now you have another special device file which sends your TPM command through the internal resource manager, but you have to also remember to reconfigure your TPM library to go through that special device file instead of going to TPM directly, because in many cases the dev TPM0 is still the default. But that's not only the end of the story, right? Now, if we zoom into the TPM library, there is actually like two major competing implementations, like Intel Trusted Software Stack and the IBM Trusted Software Stack. They eventually do the same thing, but with a completely incompatible APIs, right? So if you develop your application based on one stack, it's not that easy to migrate to another stack, for example, to distribute it on system where one of the stacks is not available. And of course, and these are kind of C level libraries, but some frameworks like Go do not really like C dependencies and not any dependencies as well. So for example, in Go, Google developed their own pure Go stack called Go TPM, and I would assume like other languages might follow, like Rust. I didn't research that, but I wouldn't be surprised Rust has its own like software stack and something like that. So yeah. And even if you select the most popular one, Intel Trusted Software Stack, like this is the official screen from their website. So it contains a lot of components. You have to understand how it works. And like from an application developer, it's just really, really confusing. Like, to understand so many concepts to actually just integrate simply with a TPM, right? But okay, you spend the effort to figure this all out, and you're finally ready to write your code and interact with the TPM, and you most likely get permission denied. And why is that? Like, for example, this was copy-pasted from the standard bare-bones Debian installation, so by default, both the TPM device file and TPM resource manager have like only allow root access to talk to it. More confusingly, if you do install the Intel Trusted Software Stack, the system will create a dedicated user and group for you. So like now you can, if you're part of the special TSS group, now you can talk to the TPM device. But from an application perspective, it's still confusing. Like if you're using Go TPM, for example, should you still pull in the dependency of Intel Trusted Software Stack to reconfigure the system? Or now you have to think about how to properly package your application to a particular distribution for it to actually reconfigure the access for you. And for example, if some user just downloads a piece of code and runs as a regular user, like interactive user, so that user has to be in the TSS group, which you cannot predict if it's true or not. So this is all these complexities. This is why we don't see wide adoptions of TPMs in user space applications these days, at least on Linux. So there has to be a better way, right? So now, there might be, right? So, and this might be the Linux kernel key retention service, also known as key rings from man pages or key store. How many of you know that Linux has a key store? Oh, cool. Depends on, this is very specialized event. Many people, like at least almost 40%. So yeah, the Linux key store is quite simple. It's just another subsystem of the Linux kernel. So you have like applications, you have the Linux kernel, and what it provides is a 3 system calls to the kernel, which applications can use to provision cryptographic keys inside the Linux kernel as kernel objects. And the advantage of that being a kernel object, it has like, the key now gains like a permission model like any other kernel object and is subject to LSM checks and everything. And originally this subsystem was designed to actually for applications to share cryptographic keys with kernel itself for in-kernel crypto operations like disk encryption or file system level encryption, because like, that user types a password, that password goes inside the kernel, and the kernel actually does the disk encryption thing. But eventually it was extended that application can also use as kernel key objects for their purposes. And the advantage of this approach is basically these system calls are available to any applications. There are no like silly permissions and group checks or device files to care about. So like any application can use it, even like containerized applications can use it. All right. And inside the kernel, the keys are categorized into basic two types of objects. There are key rings, which can contain either key rings, and these other key rings can contain keys. So it's kind of like a file system level structure. So keys are actually objects that contain actual cryptographic material or a reference to it. And key rings are like directories. So keys are like files, and key rings are like directories. So it's a collection of keys, basically. But unlike a file system, for example, a key can be simultaneously in several key rings. So like, for example, two users can have a reference to the same key. So here is a simple example of the key store functionality. Imagine we have a system with two users, Alice and Bob, and as you can see, these users do not share any like common credentials, so they're not part of the same group or anything, like totally independent users. And now imagine Alice can actually provision a secret to the kernel as a key. The secret byte is hunter2, and I try to color the output. So like keys inside the kernel represented by serial numbers. So this like number is kind of a unique ID of the key. And imagine like now Alice wants to share the secret with Bob. So what Bob can do here, Bob can create a new key ring, call it from others. And what Bob can also set permissions on that keyring to write world writable access. So world writable access to a keyring means anyone on the system can put keys in that keyring. So once that access is granted, Alice can move her secret from her own keyring to Bob's keyring. And now we can see Bob can actually access the secret without any other shared credentials. Because Bob, if we see that Bob has this key in one of Bob's key rings. So that's why Bob can access the secret. And because the secret was moved, move is not actually an in-kernel operation. Move means link the key to Bob's key ring and unlink the key from Alice's key ring. So, but in this case, Alice does not possess the key anymore, and Alice does not have access to the secret anymore. But simple secret sharing. Clear so far? In terms of keys, there are different key types in the Linux kernel key store. So far, we've been using user keys. It's the simplest key type. What it basically does is, let's say you have a process which has some plain text secret or a key. The process can provision that key inside the kernel, and another process, or the same if it has appropriate permissions, or the same process, they can read the key back. There is also like a logon key type, which is very similar to user key, but the only difference when a process provisions the key inside the kernel, that key can never be read back. So why does this key type exist? It's mostly useful actually for the original purpose of the Linux kernel key store, to share cryptographic material with the kernel itself. So like, for example, if you're running a modern Linux distribution and you use disk encryption, you may notice that the disk encryption keys were provisioned by cryptsetup tool as logon keys. So once you put it in the kernel, actually the user space doesn't need to access that material anymore, and while your system runs, it stays inside the kernel. There is also like an asymmetric key type. So imagine now the process has an RSA key, like a RSA private key. So the process can provision that private key. And another process, if it has appropriate permissions, doesn't have to read the key back, but it can reference the key and ask the kernel to perform some cryptographic operations with it. So like either decrypting some data or signing some data. And as you can see in this model, like it kind of turns Linux kernel key store into a somewhat like software HSM, right, for processes. And being the software HSM model, it will be natural if we can somehow integrate TPM there, right? So, Linux has this concept of this HSM, and like, how do we bring TPMs here? It's actually already somewhat integrated, but in quite limited fashion. There is another nice key type called trusted keys. So going back, in this model, the biggest problem here is that application provisions a plain text material, plain text cryptographic material directed to the kernel. So our idea is that because we want to remediate this kind of type of heartbleed attack, right, we don't want any cryptographic material ever be exposed to user space because it can accidentally leak. And for that, for example, the kernel key store supports trusted key. So in this case, the process uses not like the plain text cryptographic material, but an encrypted cryptographic material. So the key is actually encrypted to this machine's TPM, and when the process provisions that key inside the kernel automatically unwraps the key with the TPM. So the plain text cryptographic material exists only in the kernel address space, and if the process tries to read it back, it gets automatically wrapped again. So the system doesn't allow you to have plain text material in user space. But recently it wasn't really very useful because, if you can't read the plain text material, what can you do with that key? And until recently, basically nothing except using it for in-kernel subsystems like disk encryption or file system encryption, because the plain text key only exists inside the kernel. Confusingly, Linux has another subsystem called Linux Crypto API, which allows using Linux kernel as a crypto library. So the way how it works is a process can create a special crypto socket, and it's not a network socket. It's basically a socket that connects the process to the kernel, and that socket will be bound to some crypto implementation, for example, AS. So then the process has some key, wants to encrypt some data with the key. So the process applies the key through that socket to the kernel. The kernel puts it instantiates that key. And then the process can write some data to the socket, and the kernel will encrypt the data, and then the process kind of reads the encrypted data back. So this whole concept allows us to use Linux kernel as a crypto library. The problem with this approach, this is a completely different subsystem. So, and this key here is not a kernel key, it's just like a buffer with plain text cryptographic material. So it's not any way connected to the Linux key store API. So we realized that concept and we wanted to bridge that gap. And recently we kind of submitted the patch upstream to actually allow instantiating a crypto socket with the key from the Linux key store API. So now, for example, you have the process 3, which wants to encrypt some data with the already provisioned key. Again, it can create the crypto socket as before, but instead of supplying the key material directly, it can reference an existing key in the Linux kernel by its serial number. There will be some permission checks as well, and then the kernel will, instantiate the key inside, and then we can encrypt and decrypt some data. And in this way, now the wrapped keys are becoming more useful because you can instantiate a TPM key, and then the process actually can use that key to encrypt and decrypt data without being exposed to the plain text cryptographic material. And it was merged in Linux 6.2, so it's available from a 6.2 kernel. The drawback of this approach is that wrapped keys are just encrypted byte blobs, so they are by nature asymmetric keys. So you cannot actually do asymmetric operations with that key. You can only encrypt and decrypt data symmetrically, but you cannot sign anything. While preparing that presentation, by the way, I wanted to do a proof of concept to actually bring asymmetric support to that system, but luckily, I didn't have to do anything because someone already did it. So there is a work ongoing to actually bring asymmetric support to wrapped keys inside the Linux kernel key store. And hopefully, I think the maintainers mentioned they target to merge it by Linux 6.11. So Linux is now on 6.10 RC series. So there will be 6.10 stable release, and then the next stable release will likely have that support. And the way how it works is basically we go back to the asymmetric key model when we have the RSA key. So, but instead of plain text RSA private key, it will be an RSA wrapped key to the TPM. And when provisioned inside the kernel, unlike the trusted keys, it won't be just unwrapped. It will be just a cryptographic handle to a key inside the TPM. So, for example, when the application wants to perform some cryptographic operation in it, it will talk through that handle directly to the TPM. So the key will be loaded onto the TPM, and when you want to sign data that request will be forwarded to the TPM, and the TPM will sign the data. So in this case, it's even better. So the plain text will not be even visible to the kernel itself. Clear so far? However, this schema still has some drawbacks, right? So, and the whole concept of wrapped keys, for example, for our use has the biggest drawback. Just to give you a hint, we run many servers across the world, and most of them are, we call them either ephemeral or immutable. So like the server state is kind of disposable most of the time. And this creates a problem for wrapped keys, because the way how wrapped keys are created, like asymmetric or symmetric ones, so you have a random number generator, you generate an application-specific key, and then technically you use the TPM to wrap that key right into the encrypted blob. Which presents not, like, even though the security here is good now, like, if you don't have access to the TPM, you cannot never decrypt the key, you still have the key management problem. So once you have this encrypted blob, because like the kernel itself doesn't give you any persistence guarantees, you have to, if you want to reuse the same key, you have to like store it somewhere, right? So, and operating a large distributed network, like oftentimes we have like disk failures, broken disk, accidental wipes, and some, like I could see another use case in small IoT world where you have either diskless installations of small IoT devices or IoT devices with immutable file systems. So you cannot store this wrap key anywhere. And also like the scalability problem is there. So again, for one key, you can figure something out. Once you go to the model, like every application wants to have unique key, you can like create many of these wrapped blobs, and you have this all extra state you have to manage somehow. And it's not like an easy state to manage because these are cryptographic keys, so they have elevated requirements of maybe they need to be backed up or something like that. What if we slightly change the model how we create keys? So instead of generating a key, an application unique key, and encrypting with the TPM, what if we just take the TPM seed? So if you're familiar how TPMs work, every TPM has we were talking about TPMs 2.0, by the way. Every TPM has a storage seed hierarchy, right? And it has an on TPM key derivation function. Yeah, and it's all part of the TPM, so there is no external entities. So you have a seed, the TPM. To generate an application-specific key, what we can do is take some application-specific metadata, right? Or I call it salt or whatever mix in, and you can like shuffle into the KDF, and you can get an application unique key. And this process is really, really scalable. So like you can generate one key, you can generate many, many keys. But the advantage of this approach, and like every application will have a unique key, but the advantage of this approach is state is completely disposable, right? So as long as you have the access to the TPM, you can always recreate all the keys you need, and you don't need to actually store them somewhere. So imagine, for example, you have, again, a small IoT device with an immutable file system which allows SSH access, and you want it to have a stable SSH server key, right? So you can use that process to generate that key, and you can regenerate it on every boot, and like the users will not see that the SSH key will change, but you don't have to store it anywhere. So how to integrate this support into the Linux kernel key store? So far we've been using, in all our key store examples, we'll be using the add key system call, but there is another system call called request key. So the difference between the two is with add key system call, what the application does is basically it provides a key material to the kernel, and then the kernel instantiates the key. So the key material can be either plain text for user keys or encrypted blob for trusted keys, but the idea behind the add key, the application says to the kernel, hey, kernel, here's the cryptographic material, create the key from it. Whereas request key is different. So in this case, the application doesn't have the cryptographic material. What it can just do, it has a key identifier, and depending on your system, you can configure it as you wish, but like the kernel itself allows it to be a free-form string. So what an application does says, hey, kernel, give me my key. Give me my key X, right? What the kernel will do is it will actually create a placeholder for the key inside the kernel space. But again, every use case is different, right? So the kernel itself doesn't know how to actually create that key. So it will call a user's mode helper, locate like any executable located at asbin request key, and supply it with the key ID. And the kernel expects that executable to actually know how to create that key. And of course, now you can write that executable yourself, and you can implement whatever logic you want to obtain those keys. But instead of rewriting, the better approach is to use your distribution's ready-made implementation. And even though it's written in C, it actually supports a plugin model where, depending on the key ID, you can actually write plugins to it in any language to actually support different sources of keys. And one such source could be like the TPM. So, for example, you can write a plugin which talks to the TPM, creates or derives the key for that particular specific applications. And once that key is ready, it kind of returns that to the binary. The binary will then return the key to the kernel, and the kernel will notify the application that the key is ready. And the application will receive the serial number, and now it can reference the key or perform cryptographic operations. So, as a proof of concept, I actually wrote this plugin, and because it's a proof of concept, it's written in Python, so don't judge me too much. I will repeat the link at the end as well, but what you can do with it, you can download the code and play with it, and the way how it looks like is the following. So, once you download my script, now you can configure the request key on your system. To what it basically, this configuration means if any application requests to create a key with an ID starting with TPM2 derived something, call my plugin, and my plugin will generate that key. And this plugin actually can generate derived keys from the TPM in the same model I just explained. So in this case, by the way, this was copied from a real terminal, so consider it as a demo. But it never fails, so that's why, right? So I've implemented two modes here. So for example, you have the user space keyctl utility, which is just like a command line wrapper on the request key system call. So in this case, for example, I'm requesting a key with an ID TPM2 derived test, and I've implemented two parameters. The first parameter, 32, is like how long the key should be. It should be like 32 bytes. And the second parameter is that flexible application-specific metadata. So in this example, I implemented an application path. So like basically in this setup, I would consider that each application, depending on its position in the file system, will get an application-specific key. So yeah, you can request the key from the kernel, and we requested the user key so we can actually read the cryptographic material, and we can read the bytes. So we have an application-specific key. And to prove it works, I will actually delete this key now, because if you if you call request key simultaneously 2 times, it will actually return the cached result and not will generate a new key. So here I'm deleting the key again, and I'm retrying the operation. I'm asking the system to provide me with the key again. And if I read it back, I can see it exactly matches. And you can see that the serial number is different, so it was a different keys. But as long as this kind of proves the reproducibility of a TPM-derived key. So like, depending on, because I'm just accounting for the path of the request and binary, I always get the same key for that specific position. Yeah, and we can actually verify that. So again, I will delete the key, and what will I do is I will move that binary to another position. So it's like from user bin directory to my home directory, and I will request the key again with the same parameters, but now I get the different key. So because it's in a different file system path, and it gets a different key. So this probably would be useful, for example, for immutable system where you want to have like your SSH daemon would have a stable SSH server key, but it kind of wouldn't depend on the SSH implementation itself. For example, if you're doing a firmware update and you want to replace like OpenSSH with Dropbear, for example, it will still have the same SSH server key. So, but because it's located at a privileged location, you can be sure that like nobody can actually steal that key, right? Because to steal the key, you would need administrative privileges to put your binary into that position. Yeah. I also wanted to show that depending on the application code, like even though I have a daemon at the privileged position, but I can call it as my own user, right? So like, and depending on the code, if it generates the key at the start, I can actually steal it. So I also added a mix in a user ID here. So if I call the same pass with the same parameters, but from a different user, I will actually get a different key. So like users cannot steal keys from each other. The second parameter I've implemented is mixin parameter is a code checksum actually. So in this case, again, I'm requesting a similar key, but instead of the pass here, I'm using checksum. And again, I can read the cryptographic material. Now I can delete the key. And what I do now, I move my requesting binary from one place to another, from key CTL to key CTL2. So the pass is different now. But because I'm and I can request the key again, but it will still be the same because now I'm binding my derived key to the system TPMs and the requesting code itself. So regardless of where in the system my code resides, it can still get a stable key. And yeah, and what can I do to verify that? So I actually run strings on the key CTL, and I know it has a string called bad message for some error. So now I can hack it or patch it and replace bad message with bad massage. I'm replacing 1 byte. And if I rerun that, the same binary, but it will already produce a different key because the key is cryptographically bound to the code itself, which is also a really nice thing. The plugin also supports asymmetric keys, by the way, so you can request an asymmetric key and you can basically create some test data and actually sign with that key. Because the signatures are large, I'm also like hashing them to show that they're the same. So yeah, you can delete the key, re-request it again, you have the different serial number, but if you produce a signature, you will get the same signature. So which kind of proves that the generated key is the same. Cool. There is one drawback. So in this approach, as you may see, if you go back to this picture, we still have this problem that the key itself, at least once exposed as plain text in user space, even if within that special process has been request key, right? So it's not really well. So like it would be nice if we can like remove that middleman and basically do something like this. So like we request a key and for historical reasons I needed to change the request key to add key back. But basically we can request the key from the kernel and it will be directly derived from the TPM inside the kernel and never exposed to user space. And this is what I recently tried to implement and upstream. So like this is my patch set which I sent. Well, the initial response was mixed, so from confusion to I don't honestly believe this will ever be a solution for any possible problems that exist on this planet. But this is why I'm here, basically. If you like this approach, if you see a valid use cases, please reach out to me so I can like present more and more, evidence this might be a useful approach going further for the derived keys is actually solving real world problems. This is basically what I wanted to present today. Some conclusions. Interfacing with TPMs is hard, so that's why applications usually avoid them altogether. Linux kernel key retention service, aka key store, can be a good layer to abstract away the TPM interaction complexity from the applications. But as you just saw, it's very raw, so like some additional development might be needed. And I think TPM derived keys is a good alternative to TPM wrapped keys, providing similar hardware-backed security with potentially easier key management. And if you think the same and you want to use it now, you can use it now in existing kernels via requested key plugin, or you can wait for in kernel version if you want to make sure that the plain text is never exposed to user space processes. And probably exposing TPMs through Linux kernel key store can provide application with a very straightforward path to adopting hardware security. Because the Linux kernel key store is that like software HSM model, the applications do not have to be exposed to internals or implementations of TPMs. And probably the key store itself is a good platform to integrate other security chips and solutions. So if you're involved in developing some kind of like specialized security hardware, consider integrating it with the Linux key store. So like any application can take advantages through a simple system call interface. Here are some useful links. So the first two links are the Linux kernel documentation to Linux kernel key store, the core documentation, and specifically for trusted or encrypted keys. The third link is to the patch set, which implements asymmetric TPMs keys, which hopefully will be merged in Linux 6.11. The fourth link is an expanded link to my request key plugin, which I presented here today. So you can go and poke with it and provide feedback, or maybe submit pull request. I don't know if you can submit pull request to gist. And the fifth link is my patch set, which implements TPM derived keys directly inside the kernel with kind of same functionality as my proof of concept. Thank you very much for your attention. And I don't know, do we do questions? Can I?
Yes, we have some time for questions.
Shouldn't all this be an hypervisor service instead of an operating system service? I mean, Hyper-V, which is partially ported in Linux, has support for so-called virtual secure mode, where you basically have little trustlets that run and keep hypervisor guarded secrets. Like Windows uses this for credentials, right? And so instead of like going all the way out to the operating system, having it backed by the hypervisor may offer better like.
Well, I know I'm not really familiar with the Hyper-V, for example. It's Linux based, so it can be used the same in the same manner, but it kind of depends on how you expose that to the guest operating system. I know many hypervisors just expose the virtual TPM to the guest operating system, but that's kind of prone to the same problem.
Exactly. It should be virtual TPM backed by an actual TPM. Right? So I'm wondering if you will get better traction in the hypervisor community instead of the operating system community in really supporting better abstraction of hardware TPMs.
Maybe. Yeah, I don't know. But like, I still need to go through the operating system community because these are maintainers of the Linux kernel key storage and the TPM driver in the kernel.
Thanks for the talk and also for the kernel patches. What would happen if someone used LD preload? So you gave the example of having OpenSSH or dropbear, and that way you would get a key due to the privileged path that you're at. But if I were to write a malicious binary or write a binary and then use LD preload and then change overload the read link syscall, so when you try to figure out what is your path, you hit my function, and then I give you the path of dropbear. Then could I, as an unprivileged user, then get the key of another process?
You mean LD preload for the sbin request key?
You gave the example of using the key control you moved key control to get a different key, right?
Yeah.
And you're using that as an example for using that for SSH, like an SSH daemon.
Okay, let me find the slide.
There's like a couple slides before this, I believe.
Well, in this case, do you mean LD preload for the requesting process or LD preload for sbin request key?
Well, what would dropbear use? How would it get its key?
Dropbear will be the requesting process, right? Okay. If you LD preload the requesting process and you're using path, right? That changes nothing because you're still located at the path and you get the same key. You probably mean if you use the checksum functionality, right?
Oh, maybe I misunderstood. So request key then gets the path. Like where does the what decides what the path of the binary
path is decided in the plugin. So
Okay.
what the thing is, the way how request key works. So when the request key happens, when this placeholder is created, its information is passed to as being request key, and as being request key, for example, it has access to the requesting PID. And from the request and PID, it can go through the proc file system and understand where is the executable is located through the PID file.
I see. How does it get the PID?
So the PID is provided by the kernel.
And how does the kernel know the PID of the process?
Well,
I mean,
because
obviously it knows.
it took it from the system call.
Yeah, I guess that's what I'm wondering. Can you overload that?
No, I don't think so.
Okay, cool. Thank you.
So yeah, there is no like library call happening. So like request key knows the PID, the kernel passes the PID to the plugin, so you cannot really overload it. Yeah.
Which TPM command are you using to derive the key?
Sorry?
Which TPM command are you using to derive the key in the prototype version of this where the TPM directly generates that?
My experimental kernel patches are using like the TPM HMAC implementation, but actually because I did the Python POC later, I kind of realized I can make it simpler, so I'm using AS encounter mode. So basically, you create a primary hierarchy based on the TPM seed and the application-specific info, and that primary key is AS, and you just use it, encrypt like 0 bytes to how many bytes of the key is requested. So using AS counter as a deterministic random number generator, basically.
I see. So the Linux kernel still gets the raw actual secret out and handles it.
Yes, exactly.
Okay, thanks.
Yes.
So I appreciate you covering at the beginning like the difficulties of actually using a TPM and like how difficult it is for users. I think the TCG knows that, like that it's a really bad design where you have to read like thousands of pages of specs and stuff like that. So I run open security training, which creates free training, and the TCG recently partnered with us to make classes specifically for application developers. Like, here's easier ways to actually use this so you don't have to go through all that trouble. So my question, this was going to be my first question of like, okay, the plain text key is still exposed. So that's good that you're trying to move into the kernel even against their objections. So my second question was, you were talking about how you would derive a key, and you were talking about your particular use case at Cloudflare is you've got ephemeral servers and they need to be able to be thrown away. You didn't speak at all to the difficulties that come in that sort of architecture of, if you want to move the hosts between different physical servers with different physical TPMs, how are you dealing with, the differences of the actual different physical TPMs? Like, are you using the sort of key migration capabilities of TPMs, or are you just trying to architect around that problem?
So it's the latter one. So for example, we have like, most of our servers are ephemeral, so they keep like application cache, like a CDN workload. So you can technically throw away the cache and repopulate it later. For some of our like stateful workflows, for example, like databases, we kind of consider replication on a higher level, right? So like we don't really back up disk encryption keys, for example. What we say is like, if we have like a database replication factor of 3, for example, and if some server breaks, we just like throw it away and replicate from another. So we don't actually move the hardware encrypted data from one server to another, if that makes sense. But I could see that could be possible. For example, if you could, for example, derive an host specific asymmetric key and share the public key with another host, and then design some kind of like key agreement where you can negotiate a shared key to move data from one host to another. But like, you have to have like application level support.
Yeah. So I was thinking more of the lower level thing where you actually use the TPM, like if it's a TPM tied key and then you're trying to like, they have the capability to like move those keys between TPMs, but it adds extra security issues and problems.
Yes.
You're just saying you deal with it at the higher levels.
What I could say, like, this is where maybe trusted keys might be a little bit useful, because when you create a trusted key, you can actually mark it as exportable or not. And technically, if it's exportable, you can actually rewrap it to another TPM. But many people like think like non-exportable are better, so they still like bind it to a particular system. So if that TPM is unavailable, you cannot access it.
Yeah, that's the part I was asking about. Thank you.
All right. Is there any more questions? If not, then let's thank the speaker again.
Thank you.